What you are seeing is a nuclear device right at the table. What's happening in this is fusion, hydrogen cold fusion that happens. What happens on sun is happening right here on a tabletop version. And if you break down the materials, it has just got stainless steel vacuum chamber, a little bit of nanoparticle like nickel mesh and palladium. And what we are facilitating is two hydrogen atoms that come, generate fusion, that creates helium 3, which is still unstable, and then another hydrogen atom comes, fuses, creates helium 4, which is stable. The release of this excess hydrogen is what is generating heat.
Hi everyone, my name is Priyakshi, and today I'm speaking to serial entrepreneur Mr. Siddhartha Durairajan, who is currently serving as the CEO and co-founder at Hylenr Technologies. So Hylenr is a Hyderabad-based company that uses cold fusion technology to generate clean energy. The innovation has also received a patent from the Government of India. And in this interview, we aim to understand what low energy nuclear reactor technology is and suitable areas of deployment. Hi, Siddharth. Thank you so much for joining me today. So, Siddharth, to start with, let's just talk about what is LENR and how does it generate or amplify power?
So, LENR is an abbreviation for low energy nuclear reaction. And as the name states, it's a low volume of energy that is released. And because it's a nuclear reaction, there is nuclear fusion happening in the chamber. And this enables the fusion that happens in sun, but at a lab environment, at a much controlled environment, at a much concise form and fit factor. So that's why it is called low energy nuclear reaction. Because it happens at a low temperature. Low temperature here we mean by between 300 and 400 degrees centigrade, which is much lesser than what is required by the fusion reaction that everybody is trying worldwide, where they need 150 million degrees centigrade. So here we are doing it at 300 to 400 degrees centigrade, and that's why it is also known in the industry as cold fusion.
Mhm. And does it also have any radioactive materials, radiations?
So what we are using in this LENR devices, we are using pure 99.99 percentile pure hydrogen. So these are infused into the reactor chamber. We input 100 watts of electricity. That 100 watts of electricity is used to generate certain heat and certain temperature inside the reactor chamber. And of course, the pressure increases to a conducive point wherein the reactor chamber has something like nickel, palladium, and some more components that are put together in a form that makes the palladium lattice absorb more of hydrogen atoms in it. The moment it reaches that conducive temperature, the hydrogen molecules cross the column barrier and then fuse to each other. So in reality, what is happening is just two hydrogen atoms fusing with each other, and helium-4 is formed after multiple reactions that happen in it. So bottom line, there is no radioactive material used at all. And since the fusion is happening at a low energy level, it's like named or quantified fusion that happens inside. So hydrogen is supposed to be a consumable, but it is not a consumable because given that it can run for 2 years, 3 years with few milligrams of hydrogen. And because it is happening at this temperature, there is no emission of any radiations as well. So no radioisotopes or no radioactive materials used, neither does it emit radiations. This is the cleanest, cheapest form of energy ever produced in a lab worldwide.
Okay. And when we say energy produced, can you give us some idea as to if you, like you said, you put 100 watts, what is the output?
So with a 100 watts input, we are able to generate 150 watts of equivalent of heat, which means we are defying Newton's law and we are actually creating energy. But of course, we are working in harmony with the atomic laws. So the the fusion that happens inside, other than formation of helium, it also results in excess energy generated as in the form of heat. So that's where we are able to say our coefficient of performance COP is at 1.5. So you give 100 watts and we are able to generate 150 watts equivalent of heat. So that's in reality the highest ever anybody could generate globally.
Right. And it's a tall claim. I think you will meet a lot of speculation and skepticism about these claims. So, and I was also reading about it online and I found that to be true. So, can you help me understand what are the reasons for that speculation and how does your work address those speculations?
See, LENR is a very old subject and it's close to around 4 to 5 decades old. 40, 50 years ago, few scientists have come onto the space and then they have indeed found excess heat generation happening with LENR experiments. But the problem is they could not replicate it. They could not put a science to it. They could not put a method to their madness. And
Hmm.
when they could not replicate it, it was all tabooed or it was all stated as a one-off reaction and it could be just a chemical reaction and that's how it did not gain its momentum. So the last 10 years or so, there are a lot of countries like Japan, China, US, and the European Union. They have invested heavily on LENR.
Hmm.
So, because they realize that there is a potential in this and they realize that you are able to generate positive energy with this. So, if you have to generate a net positive energy in a regular fusion, nuclear fusion that the whole world is now attempting to, you have to spend billions and billions of dollars in generating minuscule positive energy. And none of those reactions are stable. None of them that we have tried out was, I mean, it does not give us the confidence that it is the right way to go. But the difference with LENR is, as you say, it's a very low nuclear energy power, and the only reason we could break the taboo that has been existing the last 40 years is we've been consistent with the output the last 3 years. And we've been able to replicate, duplicate in various form factors. So, say for example, we have a certain shape of a dumbbell today. We have replicated this in various form factors and we have duplicated it across different institutions. We have gone to different peer group institutions where we have shown them, we have performed the experiment in front of them, and then they have agreed that indeed it is a nuclear reaction that is happening, and indeed they found the traces of helium being formed there.
Hmm.
So that's how we've also been granted the patent. So for the first time, it has become a reality. Second, we are able to replicate. And now third, we are actually going into the application of LENR into space with our prototypes being sent to ISRO for testing. So this is a brainchild of two physicists and scientists. One is Dr. Prahlad Rao. He was known as the Missile Man of India. He worked alongside Dr. Abdul Kalam all his career. And in his journey to, so both Abdul Kalam and Dr. Prahlad had this inclination that they were always in the forefront of distractions, building missiles. So they wanted to do something constructive. And Dr. Abdul Kalam went on to co-create the stent that is goes into a heart, Indian-made stent. And Dr. Prahlad Rao went on to create a cold fusion reaction.
Right. And currently, what is the technology readiness level? Are we still at lab scale, or is there any form of manifestation of technology, like in the form of a product available today?
So, like I told you before, we are actually a week away from delivering our first prototype to ISRO for flight testing. So, the
Okay.
product is already at a technology readiness TRL level of 7, which means we are good to go. We are good to go with commercialization. So our product, our IP, everything is ready. For us, commercialization is just adapting this design to various applications that are there. When I say various applications, the space, so thermal power generation, say industrial heating. So it's all about changing the geometry form factor to fit that application, which is a normal mechanical engineering design to adapt that. So that's a no-brainer, which means we are ready for commercialization.
Right. And you mentioned a couple of areas for potential deployment, space being the one. So can you specifically for space, can you help us understand what are the potential applications this technology has?
So the space, the only thing that is scarce in space is heat, because it's all minus 100 degrees and lower is what the temperature there is. So uh, the entire energy that is being produced in space, in be it in a satellite, be it in a rover, be it in any of those orbiting space stations or anything, they produce energy from the solar panels and store it in a battery, and 40% of it is used to keep the warmth inside. When I say warmth inside, most of the electronic needs to have a temperature of around 5 degrees to maintain the integrity and keep them from freezing up and continuously working.
Mhm.
So now we with our product, we will be able to reduce the consumption of electricity or consumption of battery power by half of it. Okay, so that is one part of it. So which means any of the rovers, so for example the lunar rover, the Chandrayaan machine, after 14 days it couldn't wake up because the lunar night there was no sunlight, so there was no power generation, which means the entire ecosystem froze up. With our capability, it could have surpassed that 14 nights, and then again it could have continued for another 14 days, 28 days. It could have gone for a longer duration. So
Mhm.
that's the straightforward use case. Second is large satellites use something called as a MMRTG. It's a
Mhm.
multi-mission radioisotope thermal electric generator. Uh, it produces roughly around 110 watts equivalent of heat. It's a it's a radioactive material base. Some of it is thorium and plutonium based reactors. So once you switch on, you cannot switch them off, and it
Mhm.
generates only 110 degrees centigrade heat inside. So 110 watts of equivalent of heat. So we are directly pitching our product against it because the MMRTG is roughly around 2 feet by 2 feet and weighs roughly around 40 kilos. Ours is at 500 grams and is of a size of 15 centimeter by 15 centimeter. So in space, every kilo adds up to the cost of going up. So that will drastically change. So for us, space is a high value, high impact space, and that's what is our low hanging fruit.
Right. So in terms of economics of deploying this technology also, as opposed to, let's say, you are pitching it directly against MMRTGs. So how would you compare, let's say, bill of materials or the cost of deploying it?
So, like I told you early in the conversation, my breakdown of a bill of material is nothing but I have stainless steel reactor chamber, 15 by 15 centimeters, as small as this. I can go as small as a visiting card size uh, because I'm only using few milligrams of hydrogen.
Mm.
And then I use nickel mesh with coating of palladium. Okay. So then there is a heating element. It could be any form of a heating element that conducts it. So all of them put together in its current avatar itself will not cost more than $2,000 or roughly around a lakh and a half rupees. That's it. So if you look at the opportunity cost of selling it, yeah, I can sell it at around 1,000 crores.
Yeah, of course. Yeah, but in terms of bills of material, I think compared to MMRTG, the difference is very, very stark.
Very, very stark, and they are available in any industrial street, in any street in India. So you don't have to depend on any country for any of these material, nor do you have need of statutory licenses or requirements to procure any of these things.
Okay, just for comparison, what would the approximate price of MMRTG would be, like one unit? If
$109 million.
$109 million.
Yeah, close to around 1,000 crores.
Okay, okay, okay. So we are talking very huge potential here in terms
High
of.
value, high impact is what we can. So today, because of the high cost of MMRTG and that being nuclear radiation, you can switch on an MMRTG, but you cannot switch it off. So
Hmm,
for whatever reason, if the device falls onto the earth, everything else will burn up, but not the radioactive material. So it's a very big taboo for all of us. Most of the countries are signing up not to have nuclear radioactive material in space.
hmm,
So now, because of the high cost of MMRTG, not many people are using, say, you talk about the small nano satellites and low orbit satellites, most of them have to only depend on solar power. So every panel adds up to a kilo, 2 kilos of weight of transmission, and then the heat distribution, everything.
hmm,
Now, because it's $109 million, they have to rely on a lower footprint of the electronics to do work. Now with my this thing, I can actually eliminate number of panels and have this, because it will then facilitate every small nano satellite or even micro satellite or a medium satellite to use this for energy source.
hmm.
So 40% of their battery can now be conserved with this. So that's a big shift.
Do you have any study on the how long a system like that will last?
So we have run it consistently for 2.5 years. So few milligrams of hydrogen consistently ran for 2.5 years without any. So theoretically, it can run for uh, 12 years or almost 2 decades. So we've not done that. So we are yet to quantify most of the content that we are doing right now. So we have to quantify how much reactions are happening. We have to quantify how much of hydrogen is being consumed. So these are all something that we are in the progress right now.
Hmm. And are you exploring markets outside India also? Have you received any interest?
Yeah, very much. So we also have an office incorporated in Michigan State, and we are at early conversations with other companies in US, Europe, and other places as well. Again, across different applications, not just space, across different applications.
Wonderful. So thank you so much, Siddharth, for explaining in detail what you have done, and of course the enormous potential applications this has for clean tech and clean energy. And we look forward to more updates.
Thanks a lot, Priyankshi, and a real pleasure talking to you again.
Thank you.